Okay, so if you've tried this problem, it's pretty much a straight conservation of energy problem with a little hitch in there trying to mess you up, but there are some keywords in here that you need to look at. So what you have here is this red bead over here, and you're going to push this bead down this slide, and it's going to go through this loop, and then it's going to go up this hill, and it's going to compress this spring a little bit. Okay, so that's what's going to happen in this particular problem. The key word that you need to look at is this word frictionless right here. And because you're frictionless, that means the work done by friction, this right here, is non-existent. Which means it honestly doesn't matter how it gets from point A to point B if there is no friction. Which means this loop in the middle really doesn't matter. Okay? You could have a roller coaster going over a hill and through a loop and over another hill if you wanted to. And if all I care about is point A and point B, and a problem says we're frictionless, then none of this stuff in between actually matters. So, with that in mind, over here, this bead had gravitational potential energy initial. It was at rest, so it had no kinetic, and there's no spring, so it doesn't have any elastic. But now, over here, we are above the ground, so we have some final gravitational potential energy because we're above the ground, and we compressed a spring, so we have elastic potential energy as well. So essentially, there's your equation. Your gravitational potential energy initial is going to equal your gravitational potential energy final plus your elastic potential energy final, which then means mgh initial equals mgh final plus 1/2 kx squared. And essentially what we're looking for here is, what is k? That's ultimately what we're trying to find. Just realize, because mass is not in every single term, mass does not cancel out. But what I want to do mathematically is isolate this term, so I'm going to bring this to the other side of the equation. So I'll get mgh initial minus mgh final equals 1/2 kx squared. Now, on this side, get used to the fact that, and this is important, you have an mg and an mg in both terms. Pull that out. So you'd have mg times h initial minus h final. Okay, that's kind of useful. And I'm also going to get rid of the 1/2 by multiplying both sides by 2. So now I have 2 times that, and I'll just write down what I have left, kx squared. And then I'm going to divide by x squared divided by x squared. So then my spring constant is 2 mg times h initial minus h final all over x. Ooh, that's x squared, not x sub 2. X squared. And essentially you know everything, okay? In the problem, okay, we're given the mass, so we know that. We're given h1 right there, h2 right there, and my distance at the spring is compressed right there. So I can substitute everything into this equation, and it should be fairly simple to solve. So 2 times 0.2 times 9.8 times 1.5 minus 0.5 all over 0.1 squared. And if you do all that, your spring constant should come out to be 392 newtons per meter. Can you prove units? Okay, that's that problem.